physics and astronomy, and that was in 2013. And he did all his coursework in his first year, and then moved on to his second year, and that's when I met him. He walked into my office. He sent me an email, actually, and then I met him, and he was looking for a group to do work in. He said, okay, well, you know, you maybe work for us. And so he became interested in the kind of the laser spectroscopy work that we're doing in our lab, laser microscopy and spectroscopy, and very quickly became involved with a project that involves the use of infrared radiation in combination with near-IR to produce a nonlinear response in materials that we then detect with a visible detector. That's a whole bunch of words, and you will hear about it today, okay? But the beauty of that work is really clear. Mid-infrared radiation is radiation you can't see with your eyes, okay? And it turns out a lot of detectors can also not see that radiation, because most of the detectors that you buy, like a photodiode, for instance, or any kind of sensor photodetector, typically detect light very well in the visible, but not so much in the mid-IR. So detecting mid-IR can be done, but those detectors are very expensive and somewhat clunky and inefficient. So this is actually a challenge in the field of mid-IR radiation, in particular in mid-IR microscopy. And so Adam has explored several ways to go about that, using optical nonlinearities to solve the problem. So he will introduce two ways of doing that and show some results. Along the way, there was a lot of engineering to be done, and one of the tasks at hand was designing specific lenses that can handle the radiation in a very broad bandwidth, so from the visible all the way to the mid-IR. This is a significant challenge, and Adam solved that problem very elegantly, and then produced those lenses and used those lenses in his research. So this is a nice complete story from an initial idea to actually doing the engineering, doing the microscopy, doing some applications, and showing that these applications actually have some use. Okay, so that is the whole, I summarized basically his entire talk. I promised not to do that, and here I am. So something you may not know about Adam. You know he has great loafers, right? He wears great loafers, I'm very jealous. I was actually planning to buy a pair myself because it looks so comfortable. Okay? It looks so comfortable because he always comes into my office. Maybe this is something you don't know. Into my office in the morning, my door is usually open, unless I don't want to be bothered and it's closed. Okay? But in any case, Adam typically walks in, he looks, oh, the door's open, he just walks in, grabs a chair, and just starts chatting, okay? About all kinds of things, usually about new ideas. Oh, I read this paper the other day, what do you think about this? What do you think about that? And then he sends me a couple of links and so forth. So he, every day, almost without fail, he comes into my office with a set of new ideas, okay? Which is great. So he was very actively thinking about new ways, new things to try. Not all of those things can be done, of course, but keeping thinking about it, of course, is a great way to explore new terrain. Okay, so that's a lot of stuff. Adam, I think it's time to take over.
All right. Well, thank you, Eric. Yeah, so in a nutshell, he basically covered it. I do have pretty awesome shoes. No, I'm just kidding. They're not waterproof, as it turns out. Found out the hard way, which I already knew, but reaffirmed yesterday. Okay, so the title of today's talk is Vibrationally Sensitive Nonlinear Optical Microscopy with Infrared Light. Now, in this talk, there's quite a number of images, and these are intensity-based images. So if I were to portray these images in a grayscale, the black would correspond to no signal, and white would be the normalized maximum intensity. Now this field is very common to falsely color these pictures. That way you can identify different features in the field of view, or else label what technique was used to acquire that image. And so as we go through these pictures, remember that they're just intensity-based measurements that are falsely colored. For example, here. So I actually want to start off by showing the conclusion of the talk first. What we see here is adipose tissues. That's fat extracted from a mouse. And it was acquired using the third order sum frequency generation technique. And I'll say a couple more words on that later on. But the take home message from this is that on resonance, the lipid-rich cells have large signals, and the surrounding aqueous medium have very low signals. However, when we tune the laser of the mid-infrared to the OH vibration, then the water starts generating a lot of signal. And the lipids generate quite much less. And you can see that, in fact, there's negative contrast because the water is generating so much signal. Now, what's interesting about this is that it was captured using, like I said, the third order sum frequency generation. It's a third order process that probes the molecular IR absorption, and that's how it generates its contrast. This type of image, this technique of taking images, has never been done before. So I want to say a couple words about what we're going to be discussing today. First, a few words on the background of nonlinear optics, and then the microscope setup used to acquire these. Now, this is not a commercially available microscope. Virtually every part of it is one of a kind. Most importantly are the lenses used inside of it. As Eric said, that was basically the crux of this whole research, was getting this piece of equipment engineered so that way when we put it into the microscope, we could actually do microscopy and collect images in a way that no one's ever done before. So that was a very significant development. Afterwards, I'll show you some of the example images that were taken, and we'll show some of the results from the studies we conducted. All right, so here we have electromagnetic radiation. You've seen this before. This region right here is the visible. That's where our eyes can see, of course. And the purpose of today's talk, we're going to be focusing on the infrared. Now, that is where heat is located. Like, that's where thermal energy is. So the fact that your coffee is nice and warm is due to photons in the infrared regime. However, there's a unique property, and it is that organic molecules display characteristic absorption features in this region, and it's called the fingerprint. Because, as you can see, here is an IR absorption of collagen, and on the right we have a number of different things, protein-rich material, lipid, nucleic acids, and carbohydrates. Now, there are similarities and differences. Now, some of the things that they have in common is that in the 3300 wave number region, that's where characteristic OH stretches are, just a little bit lower. On the other side of 3000, that's where CHs are. And then over here, you get a whole bunch of different absorptive features. These are the amides. These are your COs, CCs, bending, breathing modes. So in these regimes, they have similarities, but noticeable and measurable differences. So this is where the vibrational sensitivity part of the talk comes in. The idea is that if you have two masses on a spring, they have a resonant frequency, and if you drive those masses at a frequency that is either below the resonance or above it, you're going to have a small amount of absorption. What that means is typically you have your light source and your detector right in the middle. That's where you put your sample. And so if it is on resonance, you get a strong absorption. That corresponds to, in a linear IR technique, a loss in your signal. However, in the nonlinear case, when you are driving it on resonance, all these nuclear motions are just wiggling back and forth. All this energy is really easy then to put in another higher energy photon. So if this is your mid-infrared, this is typically a near-infrared or even visible, which then gets frequency up-converted. So in the nonlinear case, when you're on resonance, you detect strong signals. So you might ask yourself, well, if you have a method of detecting linear IR, why even bother doing the nonlinear technique? Well, several reasons. As Eric pointed out, in fact, these mid-infrared sensors are low sensitivity and just riddled with noise due to thermal backgrounds. They're not nearly as efficient as silicon photodiodes. So by up-converting it, we can then detect it in the regime where you can easily detect radiation. Resolution is enhanced. Now, spatial resolution is defined by the diffraction limit, lambda over 2, and in mid-infrared, typical wavelengths might be 5 microns. So the diffraction limit is on the order of the size of cells. So if you want to do cellular imaging, you have to somehow beat that diffraction limit. This can be achieved through up-converted measurements. Because we're reliant on tightly focused light, we have intrinsic 3D resolution using this technique. And we're piggybacking off of the proven success of nonlinear Raman. And Raman is a complementary technique. It's a little more developed than nonlinear infrared, but it also can be acquired in a label-free manner. And this demonstrates the utility of a label-free microscope. Now, this is a comparison between fluorescence on top and Raman on bottom. Now, these cells were stained with a fluorescent dye, and then captured in the red frame is the actin, and the green is the Golgi apparatus, and in the blue we see the nucleus of the cells. Now, on the bottom, we see a very similar story, except for what's important is that these images were ascertained label-free. They were collected from the endogenous signals which originate from chemical differences inside the cell. Now, when we label these images on top, or when we overlap these images on top of each other, we can see that the Raman performance is nearly as good as the fluorescence. Now, label-free microscopy is good. In fact, it's really good. Labels can negatively impact the health and operations of cells. So, therefore, label-free is regarded as ideal, the best case scenario for bioimaging. And in a non-destructive way, we can image individual cells or things much bigger. That's what we see here. We see an entire gland, and this happens to be a sebaceous gland encircling a hair follicle seen here. And this was acquired over multiple fields of view, which were then stitched together. And here we can see that the very oily sebaceous gland, which makes hair oily, is made up with a bunch of lipid droplets. Now, these lipids have congregated in such a way that we can visualize where they are located. Now, however, imaging large volumetric data sets is both time-consuming and computationally demanding. Now, this is compounded when you add color for hyperspectral imaging to include spectroscopic information. Now, this happens to be a sectioning from a brain tumor, where the blue contrast is generated from protein-rich biomass, and the green contrast is from lipid-rich biomass. Now, this happens to actually be a very nice picture. It highlights the utility, the real-world utility of a label-free microscopy, and it shows the direction that our research is headed. So, okay, I want to say a few words about nonlinear optics in general. So, say you had a laser, and it happens to be a low-power laser. You're probably not going to generate many nonlinearities. In fact, it's not too common. You have to have a very tight concentration of an electric field to generate nonlinear effects. This is why, aside from green laser pointers, you probably don't come across nonlinear optics much in your day-to-day. Now, if you want to generate nonlinearities, what you could do is you could take that average power and jack it up a bit. However, if you're doing imaging, you're probably going to burn your sample that way. So the solution is to redistribute this laser power in the time domain. This way, using pulses, you can then still maintain your low average power while having high peak powers, high enough to actually generate nonlinear effects. And in our microscope, we actually use a 7 picosecond laser. That means that the time that this pulse is on is 7 picoseconds, and because it's operating at 76 megahertz, it then is off for 2,000 times longer until the next pulse of the pulse train arrives. Now, you may think, well, if your goal is to generate bright images with strong signals, could you use a laser source with shorter pulses, perhaps a femtosecond laser? If you have femtosecond, that'd be higher peak power, which means more nonlinearities. More nonlinearities means more signal. However, as your pulses approach a delta function in the time domain, when you take the Fourier transform, it corresponds to spectral broadening, and then you end up with more spectral components in your pulses. Now, this is detrimental when you're trying to do spectrally resolved microscopy. You want to maintain your spectral resolution. For this reason, we found that a picosecond source is actually quite ideal. Okay, so this is the only slide with an equation on it, so bear with me. So what happens is when you have a material and you put it inside of an electric field, the charges get displaced from equilibrium. Now this is a polarization. Now the degree of polarization is material dependent, and if you drive it hard enough, you can actually induce nonlinearities. So this is the source term for how these nonlinearities originate. And for the purpose of today's talk, it's important to focus on the second order term, shown here with the chi2, which has certain geometric restrictions and limitations. It really only has samples with a non-centrosymmetric symmetry have a chi2 response. What that means is they have to be an asymmetric system. They lack inversion symmetry. One example would be a chiral molecule. And as you'll see later in the talk, some of the samples that we image that are biologically relevant include collagen, cellulose, and some biocrystals. Now the other nonlinearity that we'll be discussing later is that TSFG that we showed at the beginning. Now this is a third order response, indicated here by the chi3 tensor. And the third order responses are much more general. They don't have geometric restrictions. In fact, everything has a non-zero chi3. So for this, we're going to be able to image various other sample systems, such as liquids and some amorphous solids. All right. So basically, in a nutshell, what we're doing is we take our two incident fields, we mix them in our sample, and in the light-matter interaction, produce nonlinearities. And what we're looking for is the transmogrified incident photons, which is indicated here by the green light. Now, if this material happens to be chi2 active, we'll see a number of nonlinearities, as we see here. Yes, we'll have second harmonic generation of both the incident fields. We'll have the frequency mixing term, the sum frequency generation, along with the difference frequency generation will also be there. Of course, there also will be third order responses. You can have third harmonic generation, or third order sum frequency generation, or this other one, CARS. I'll say more about that in a minute. So there's actually quite a cornucopia of nonlinearities that are being generated in the light-matter interaction. And for microscopy, there's a couple that are more particularly suited for microscopes, and I wanted to highlight these two-photon fluorescence and the coherent version, second harmonic generation. Now these were introduced, these were the first to be applied to a microscope about 30 years ago almost. Now these two, CARS and SRS, these are the third order responses which probe the Raman sensitivity of these molecules. Now these are important. They have vibrational resonances, and that's part of the contrast mechanism. Of course, there's also the photothermal, which also has vibrational information involved in its interaction, and it also benefits from not being detected with mid-infrared light as well. However, it probes the thermal diffusion, which, even if it's the same molecules, depending on where it is in the cell, can influence that. So for this purpose, we don't really focus on photothermal for this talk. So in our lab, the Patna lab, we are known for doing CARS. This is a third order interaction. It stands for coherent anti-Stokes Raman scattering microscopy. And what we see is that one photon excites an electron, and then a second photon then stimulates that electron into the vibrational state. Now this is a Raman transition right here. It then is probed with another photon before radiating at the upconverted anti-Stokes frequency. The contributions from the research that you're seeing today is done in this fashion, where instead of the Raman transition, we are populating those vibrational states through a direct dipole excitation using mid-infrared light. And in the second order, the lowest order interaction, the Chi2, we have the mid-infrared photon followed by one pump photon. Now, that TSFG image that we showed was acquired in this fashion, where we have the same mid-infrared photon, but instead of just one, we have two upconverting photons before detecting radiation. So this is what we're looking at. All right, so let's take, the SFG, okay? It's the lowest order nonlinearity with vibrational contrast. It's been around, this technique has been around since the 80s, ever since Professor Shen introduced the technique. And it's, by and large, has been implemented in the same way ever since, where you have your two photons, a mid-infrared and a near-infrared, which come in at different angles to facilitate phase matching for higher signals, then interact with the sample at the interface of your cover slip. They then mix with your sample, and the upconverted frequency is sent off to the high-sensitivity photomultiplying tube. All right, so that's SFG. However, literally every other nonlinear technique is implemented in this fashion, using a high numerical aperture objective lens. So what's with that? Why is it that SFG is used in this fashion, where every other nonlinear technique puts it in through an objective, brings it to a tight focus, and in a collinear excitation, generates a signal in that way? Well, it has to do with the optics. So objective lenses are exclusively engineered for the visible and the near-infrared light, never mid-infrared. However, in order to do these experiments, it's a necessity to accommodate the mid-infrared radiation. There is zero transmission through these objectives with mid-infrared light because they're made out of glass. So the solution is to use a reflective objective, mirror-based. This way, we can use our mid-infrared because mirrors are inherently achromatic. They treat all colors of light the same. So they're great for broadband applications. And basically how this works is you send in your light. Of course, there's that first mirror, and if it's on axis, the center contributions then gets reflected back down. However, the chief rays propagate onto the secondary mirror, which brings the light to focus. All right, so here's the objective lens that we use in our experimental setup. It happens to be a modest numerical aperture of 0.65 and has a magnification of 74. Now, typical objectives with a comparable numerical aperture might have magnification factors of around 20 or so. Now, what this means is that in our field of view, using this reflective objective, our field of view is much smaller. So we don't get to see as much of the sample as we would at any given time if we were to use a refractive-based lens. So when we look at the physical optics now of the lenses, we see that in the refractive case, we see a nice Gaussian beam profile at focus, where this is about a micron. And this is in the lateral direction. However, because of this central obscuration, we see that the intensity of the energy at focus is not just in a tight Gaussian distribution. We see these annular rings. This is energy that's not brought to the tightest focus possible. And when we look at this in the axial direction, so in the Z direction, again, we see that the refractive case has a much tighter focusing, about 1.5 microns or so. And because of this center obscuration, the reflective lens has a focal volume that in the Z direction is about 15 microns, 10 times worse. And depending on who you ask, you might say that this focal volume either looks like a cigar or a hot dog. All right. So here's our experimental setup. We have our laser source, which then seeds our OPO, our tunable laser. This is how we create our tunable laser. Over here, this is where the reflective objective sits that I just discussed. Okay, so we have our lasers. They get combined using dichroic mirrors and sent off to the microscope. Now, before I joined the lab, there was an SFG table in existence, had this OPO laser, but they were collecting images using stage scanning. And what that means is the laser beam was fixed on axis, coming to focus through the objective lens. And what they would do is take the sample stage and then move that. And you could collect a 512 by 512 pixel field of view in about a minute. However, that's not that fast, because we need to collect multiple images and then average them together, so that way we can get a nice signal to noise ratio of our images. The solution is to use a beam scanning setup. And what that means is, rather than moving the sample, you fix the sample and then just raster scan your galvanometric mirrors. However, as your laser scans, it's going to miss the back aperture of the objective unless you have an optical relay system in place. And that is what we'll talk about next, the lens design. What these lenses do is they're able to map the second mirror, the surface of the second mirror, onto the back aperture of the objective lens in a way so that as you scan, you're then able, as it approaches the back aperture of the objective, it'll come in at different angles, but it will have a constant intensity as you illuminate. Okay, so I'm gonna say a few words about the design of these lenses. So here's a familiar image. You've all seen this before. Yeah, sure, Pink Floyd. But at the same time, this is also chromatic dispersion. What we see is that there's a wavelength dependence on the index of refraction. What that means is that in this particular case, different colors see the material as having a different index of refraction. And the different glasses, to which there are 200 or so in the visible, have different properties. So if you have a flint material, that means there's high dispersion. That means the change in index of refraction is very large. However, fluorites and crowns more generally are the opposite. They have a very narrow change in index of refraction based on the color. How this manifests itself inside of the lens is seen here. On the left we have a flint, which means that there is a strong dependence on the effective focal length, depending on what color of light you use. And on the right, we see a fluorite, which has a smaller dependence. Now, we're doing precision microscopy, all right? We're not interested in small differences. We want to eliminate the chromatic effects, aberrations. And this can be achieved using a doublet rather than a singlet. And here you have, in the preferred implementation of a Fraunhofer doublet, you can have your positive lens in the front, which would be a crown material, followed by a negative flint. And this way you can have color correction. And that's what we see here, is that as the three colors of light propagate through, the red and blue colors come to a perfectly matched focal length. And because it's a doublet, it can only accommodate two colors at any time. Therefore, the green and other colors aren't exactly in the right focus. But nonetheless, the chromatic aberration as a whole is minimized compared to the singlet. All right, so I designed some lenses in ZMAX, and the materials that I selected was calcium fluoride for the crown and sapphire as the flint. Now, I know sapphire may sound expensive, but as it turns out, it's actually a very commonly used substrate in the field. And there are associated costs with the machining, but as far as the crystallinity goes, it's not that big of a problem. So we're putting these lenses into a commercial beam scanning laser system, the FlowView, made by Olympus. And so therefore we wanted to match some of the optical properties of the standard optics that were included in the device. Therefore we're using a 50 millimeter focal length lens at the front, the scan lens, followed by a 180 millimeter focal length tube lens. And this plot shows the chromatic correction. of the singlet versus the newly implemented doublet. What this means is that if you had a lens with a nominal focal length of, I think this was 150 millimeters, then you'll see that in the singlet case, the effective focal length for a 1 micron wavelength at 150 millimeters is offset by 1 centimeter or 10 millimeters, just by virtue of it changing the color to a 5 micron source out in the mid-infrared. Now what we see is perfect color correction between the 1030 and it's about like 4.2 microns or so, and the secondary color, the total deviation between this given spectral range is less than a millimeter. So this is indeed quite an enhancement in optical performance. One last thing is that there's never been a lens with this engineered for this spectral range. Typically you either get lenses that are visible or near infrared because they're made out of glass, or you get mid-infrared achromats, which are made out of silicon and germanium. And never before has the lens been designed to bridge that gap between the near-infrared and mid-infrared. So you couldn't just buy it. That's why I had to go through all this trouble of designing it. Okay, so on-axis performance. Here we see a plano-convex calcium fluoride singlet, and how to interpret these things, because they're on the next couple slides, is the dots represent energy distribution, and the black circle defines the diffraction limit, or the Airy disk. And so if there's any amount of energy inside of this, it's the same as saying that it's at the diffraction limit. And so the singlet is in fact it's pretty good concentration of energy at the 1 micron wavelength. However, like I said, when that 1 micron is at focus, the 5 micron radiation is not. That's why we see this huge amount of energy outside of the diffraction limit. And in the doublet case, both those colors are in the diffraction limit at this point. And in general, for an f5 optic, a singlet lens has a spot radius of about 25 times that of a doublet. Okay, well, what about off-axis? Because again, we're talking about beam scanning optics. So you can't just think about on-axis. If it was just on-axis, you may think about using a off-axis parabolic mirror, a reflective technology shown here. Okay, well, here's the doublet, there's the mirror. On-axis, we see that both of them are within the diffraction limit. But once we go off-axis, on the beam scanning at a 5-degree angle, the refractive has, sure, it's not diffraction limit anymore. You can see that the energy is outside of that circle. However, in the reflective case, it's worse, much worse. That circle is in the middle here. And so, even though it's achromatic, there's one color, but you can see that that energy distribution is significantly beyond the diffraction limit and just has terrible imaging performances. We tried to do this, set up the laser using this technique, and it was just not, signals weren't being generated. Okay, so yeah, we designed them, we ordered them, here they are. See a couple lenses, these that were manufactured to the prescription with the associated tolerances that to ensure that they were still manufactured affordably. And we put them in the microscope. Okay. So this is a USAF test plate, and it's commonly used to quantify the performance of the image, or of the imaging system. And this is in the sample plane. Now, using the scan tube lens singlets, when we use the 1030 radiation and bring the system into focus, yeah, it has nice resolution. However, when we switch the lasers to the 3.5 micron source, it's very blurry. Poor imaging performance. But when I swap them out for the doublets, it's as clear as day that when the 1030 is in focus, the 3.5 micron is basically in focus as well. So there is a significant improvement. But we're talking about nonlinear optics. This would be kind of like a linear resolution. What about Nonlinear, how does this manifest itself into generating those other signals? Well, this is my second favorite picture of the talk. And you can see why. This is calcium fluoride singlets on the left, doublets on the right. The improvement is palpable. You see signals generated in regions that were otherwise dark. The regions that are lit up have enhanced contrast, enhanced signal as a whole. Finally, we have the tools in place to do some sick experiments. And that's what we see here. So this is a representative, now we're going into the bioimaging part of it. So this is a representative images of collagen, very relevant biological sample. And on the top, we see the images acquired in second harmonic generation. And sure, yeah, we see bright signals when the polarization of the mid-infrared beam is aligned along the long axis of the fibers. And when we rotate that, the polarization of the near-infrared beam. And when we rotate the polarization to be orthogonal to the long axis of the fibers in panel B, of course there's much less intensity. And this can be mapped out in a polarization plot based on intensity shown here. So as you rotate it, intensity changes, okay? Well, on the bottom, we see the same field of view captured using some frequency generation. There's a couple of things to take note. First, there's enhanced contrast. Maybe you can see that the striations from the fibers are indeed much more resolved in the SFG technique, and that's because the resonant contribution to the Chi2 response has asymmetry, a strong asymmetry. We're generating signals only where there's good amounts of fiber. Now when we rotate the polarization of the mid-infrared, we see a similar story to SHG, reduced intensity. However, what you don't see in SHG is what's highlighted in panel F, a spectrally encoded difference in the molecular orientation of the collagen molecules. So with this, and this is highlighted in more, this is shown more readily here. How to interpret this is we took the image stack, the spectral stack, sent it through a computer program which does a linear unmixing of the spectral responses, and it associates the pixels with its the retrieved spectrum. And what we can see is that in this bright feature here, on the last slide, now displayed in red, it shows a fundamentally different spectral response than that of the rest of the fibers. I'll go back a slide. Because when the mid-infrared beam is aligned along the long axis, that feature is pretty much missed. But by detuning, or by rotating it, you can see it suddenly light up. Now this feature is indeed here, it's just that there happens to be a bend in the fiber that you can only see by either doing rotation of the polarization or by looking at the spectral response. So we're able to, just by merely changing the color, gain information onto the molecular orientation of the sample. Of course, we're also able to image other samples as well. This happens to be packed granules of cellulose. And on the top panel, we see that this is indeed taken with the SFG technique. Right next to it, that's the second harmonic generation. And on the bottom, we see a very similar story to what we just saw on the last slide. We see an unmixing of the various pixels and the corresponding spectral responses. And the virtue that there are regions that light up when we tune to non-resonance of 2945 wave number. And then we see other regions light up when we tune to 2965. Shows that there is a difference in the packing structures of these cellulose. As these granules were combined, they got packed into different organizational geometries, and this is encoded in the spectral response. Of course, we're also able to image other samples, including cholesterol crystals. That's what we see here. Again, we see another polarization plot, but more interestingly, we see a very interesting SFG response. Now, there's a number of peaks in this, and this is all within that CH region. We see a number of peaks. That's because the cholesterol crystals are triclinic. They have many ways in which that you could have a non-zero Chi2. And one thing that we saw that was fairly remarkable was that as we were tuning, they didn't all have this bright peak at 2845. That's this region. What we saw is, in fact, that some crystal regions had the brightest peak here. Some of them had the weights of these resonant peaks shifted. So that way, that's shown here, that some of these other crystals coming at different angles, perhaps this resonance was the tallest one, and that this one would be more subdued. And similarly, in the green channel, these back ones, was actually the 2965 peak. So again, we're able to look at a difference in the spectral response based on the molecular orientation. So this is a nice pretty picture. This is more cholesterol crystals. And what this slide emphasizes is that the sum frequency generation signal on resonance is strong. CARS is regularly used and implemented for a whole bunch of applications. And what we see here is that the SFG signal is comparable. All right. Well, that's it for the second order technique. Let's move on to the newly discovered third order sum frequency generation. So this was the first images that we collected using this technique. Eric had this idea of, well, why don't we go explore, see if this even exists. And it wasn't until we had these new lenses in place that we were able to generate a tight focal volume that was capable of producing this third order response. So this is in fact, the first presentation showing some of the bio applications using this technique that we'll get to in a couple slides. So on top, we see oil droplets in D2O imaged using the CARS technique, and on the bottom, TSFG. Now, there's some differences, but also some similarities. And what we see is that off resonance, I know it's really hard to see, but in fact, we see negative contrast, similar to what we saw in that first adipose image. And that's because the oil droplets themselves are having a destructive interference between the resonant and non-resonant contributions in the oil, and the heavy water is now generating more signal, and you see negative contrast. Now that's not what we see in TSFG. Here we still have positive contrast, where the oil droplets are still generating more signal than the water background. However, when we tune on resonance around 2845, both of them light up and have nice strong intensities. Now, the fact that this has negative contrast and this has positive isn't too surprising when you look at the spectral response of the two modalities. Now they're probing the same lipid droplets, however, as you can see, they have a different spectral response. CARS is already a nonlinear process with a dispersive line shape compared to the linear Raman. And the TSFG is even more dispersive, has even a larger non-resonant contribution. Therefore, it's not as surprising when we see positive signal off resonance. That'd be the non-resonant contribution. The point spread function of the different techniques are what give it, which is what defines its spatial resolution. Again, we're using mid-infrared light. However, as we can see, the TSFG technique has enhanced resolution from the SFG, and this is because it is quadratically dependent on the focal volume of the pump beam, and we're able to achieve spatial resolutions of about 450 nanometers using TSFG. About an order of magnitude better than what commercially available FTIR microscopes can achieve. SFG is about 650 nanometers, and we see that SHG and CARS are about just under 600 nanometers. So the higher order the nonlinearity, the greater the localization that the signals were generated from, and therefore the tighter the point spread function. Here we see the cellulose granules that we saw earlier, but now imaged in all four modalities. We have the CARS, SHG, SFG, and TSFG. So finally, we've introduced two mid-infrared techniques into the family of nonlinear optical modalities implemented into a beam scanning microscope. So here's that adipose picture that we saw at the start of the talk, alongside the CARS counterpart. On the bottom, we see that adipocytes light up with strong CARS signals, and again, we see negative contrast. Now, if CARS already exists, and we see similar features, why bother going through all this work of creating these lenses and doing this microscope and to get TSFG when CARS already exists? Well, it has to do with the orders of magnitude that these things operate, all right? So CARS is reliant on a Raman transition, and Raman is a very, very weak interaction. However, IR absorption is much stronger. How much stronger? About 10 to the 10 more likely to get an IR absorption than to undergo a Raman transition. Now, this is strong motivation to pursue this direction of research for upconverted signals that are dependent on these highly likely interactions, using mid-infrared light to obtain your contrast. All right, now this is actually my favorite picture of the talk. What we see here is, this is meibomian gland, which is in your eye, and it's used to lubricate your eyes so your eyes don't hurt when you move them around. And again, it's loaded up with lipids. This is oil droplets, image extracted from a mouse, and imaged again with TSFG and CARS, surrounded in D2O. And again, we see similar responses between the two techniques. We see bright signals on resonance and detuning to off resonance, low signals. Now this is our real-world application of label-free multi-photon microscopy. We're actually able to do studies now using this new technique, and this has bolsters strong confidence that it can be applied to many other techniques, many other applications. All right, so we have these mid-infrared pulses. We threw them into a microscope, saw a number of responses, nonlinearities generated using mid-infrared light. But a peculiar observation was that we actually saw that these mid-infrared beams had an effect on some of the other nonlinearities. Particularly, I was aligning the microscope for a CARS measurement, just getting the beams lined up, and I didn't block the mid-infrared beam. And serendipitously, I saw a increase in signal when I blocked the beam. That means that when I had the mid-infrared beam there, the signal went down. That's what we see here as the mid-infrared. So we did a measurement. We did a couple measurements. We had our oils, we had them tuned to the CARS resonance, and then we increased the power of the mid-infrared beam, and the signal went down. Finally, we have a handle on how to manipulate the CARS signal. The way to think about this is that the material is in the ground state, and it needs to go through a Raman transition to get to that vibrational state in order to do the CARS process. However, if you have your mid-infrared beam there, you can depopulate the ground state by putting them into that vibrational state already. If they're already in the vibrational state, they can't go through that Raman transition. That is why we see a CARS depletion of the CARS signal by increasing the mid-infrared power. Now, this has perhaps some interesting applications. By implementing the mid-infrared beam into a vessel beam, we could then do a label-free version of STED, which would, perhaps you know, super resolution implications. All right, so we're at the end. So here are your take-home messages. One, by probing the nonlinear properties of these samples, we're able to use mid-infrared light and instead of detecting it in a linear fashion, upconvert it to easily detectable signals in the visible or near infrared. The third order response works. Now we knew SFG worked. That's already been done in a microscope in a collinear excitation. However, the research that you saw today was the first discovery of the third order some frequency generation. And we're using, like I said, mid-infrared light, and we're achieving sub-micron resolution. Therefore, we're able to gain spectroscopic and spatial information. And this is similar to FTIR microscopes. However, we're able to do it at over 10 times the resolution, which means that it can be applied to individual cells. And this is actually the beginning of much more. Now, this is a new type of microscope. This microscope has tons of room to explore. If you remember at the second slide when I showed the different IR absorptions of collagen and the other samples, and there was like that OH and CH region, well, that's the only region that our laser is currently capable of probing. Our laser source only goes out to about 4 microns wavelengths. But all those other interesting features are further out into the IR, out into like the amides are at 6.5 microns, and many of those other strong features were out at wavelengths as far as 10 microns. Now, when I say that this is the beginning of many more things to come, this summer, Eric threw together a NIH proposal for a $1 million grant to continue my research. And though he hasn't actually been cut the check yet, I did get reviews of exemplary status, so it's highly likely that this project will continue to move on, and a big part of that will be getting a new laser source that can then accommodate light generation at these redshifted frequencies. Now, we suspect that while we were probing the CH region, and that we were able to see chemical contrast in that zone, the idea is that by shifting to the protein resonance over at that 6 or 6.5 micron range, we'll be able to generate, there's much larger IR absorptions, which will translate into much larger signals. And the utility of this technique may find a footing in that regime. So this is some of the directions that we think that we really might have an impact. So I'd like to thank my schools. University is a great place to be. And I'd like to thank my funding agencies because I didn't have to pay for grad school. And, it was great. Of course, in my time here, I had quite a lovely experience in the Pommel lab with all my friends and lab mates, especially Richard, who was my co-author on a lot of my papers. During the lens development, Eric and I spent some time at the Cove on campus where we pursued the commercialization of such a lens. And these guys at Supply Chain Optics were our collaborators that we met through the optical professional group called OSSC, Optical Society of Southern California. And through our networking, they've been integral in the fabrication of these lenses. And what was I going to say about that? Oh, so we're pursuing commercialization. Now, I did just spend my entire life in school, and this is the end of it. So no more PhD. So one might ask, well, what are you doing afterward? Like, what are your plans? Well, I'm not exactly sure. Part of me I want to stick around and help train the next group of students that take over my table. At the same time, pursue the Trestle Optics company that I started. And here we're going to be retailing optical components that are designed for the mid-infrared. And we have a number of optical ideas in mind, and these guys are helping us get them manufactured, and then we can partner up with some of the big retailers such as Edmund Optics, and then get them into the community. And with that, I'd like to thank you for your attention, and I'll take your questions.
That was fresh off the press.
Yeah, I went bowling last night.
All right, any questions for Adam? Come on, guys. Some difficult ones, please. He needs it.
What do you think your first step will be in pursuing the Trestle Optics program?
Supply Chain Optics just put our delivery of the first lenses back 2 weeks, so they'll be here December 20th. After that, we're I know exactly what we're gonna be doing. We have a couple experiments that we've done. We're gonna redo them using the new lenses, and then some of these measurements include doing an SFG. You guys don't need to know the details, but we're gonna put out a publication of the lens design, which we will then include when we send off the prototypes. And we've already networked with the Lars's position is the manager of optical components. He's in charge of getting like new things into their catalog. And so we've spoken with him over the last several months, and so we think that that will be a good first step. Not doing this ourselves, but rather by selling our products through the big players in the field.
I guess, so when you designed the doublet, did the biofringence of sapphire, like, does that cause any differences?
Yeah, of course it does. So actually, we ordered some lenses about 2.5 years ago, and I neglected to inform them that what we want is a C-cut sapphire. Sapphire is uniaxial, though it's birefringent. If you align that crystal structure to be on the optical axis, you can then eliminate the effect of birefringence. Because you're right, we're doing polarization resolved microscopy. That is an effect. But it is easily achievable to eliminate that effect by purely indicating to the fabric, to the supplier, that what you want is a C-cut sapphire. Yeah.
So your microscope is set up for 3 beams.
Yeah.
At the moment, no more than 2 at a time, but as you presented in your presentation, there are some possible applications for adding in the 3rd beam. Would it be, do you think, would one of the next steps be going from a doublet lens system to a triplet lens, or would that add too much cost and difficulty?
Well, see, we do 2 beams at a time because of the nonlinearities that we want to probe at any given moment. If you recall that, 1 second, just go back. There we go. All right, so this is the chromatic shift, and when we do our spectral sweeps, we're focused into about this region. There's not much of a chromatic shift here, all right? It's pretty much the same. Now when we do the cars, we're using 1480. That would be about right here. But we're also using it in conjunction with the 1030. So again, that's not that much of a focal shift. So when we're doing our studies, we find experimentally that there's not that much of a difficulty in having high performance just by using beams that aren't at the design specification. That's fine. Therefore, I don't know if there's a necessity to go to a 3rd order implementation. I think that you'd be over-engineering at that point.
Any questions? You guys understood everything?
Thanks.
You guys understood everything? You're like nodding, like, uh-huh, that's what I thought.
Many of the pictures are very familiar and photographs.
Very good. Okay. Well, with the blessing of Mom, I think, let's thank Adam one more time.